All right, and we are alive again. All right, and we are alive again. I think the chat got cleared. Shit. No. Damn. If anybody happens to have the... Sarah, if you had those things saved from before, I think I remember what they were for the most part. I hope they were saved though. Okay. Sorry about that. Alright, so we're gonna get started. Okay. Sorry about that. Alright, so we're gonna get started. Okay. Sorry about that. Alright, so we can start with a knights and knaves problem. We're gonna get started. Okay. Sorry about that. Alright, so we can start with a knights and knaves problem. Okay. You got it. Okay. So... I will put the problem in the corner of the screen. Alright. I'm gonna find a good one right now. Okay. Okay, I'm gonna pick one from that same, probably from the same website that Adi got his from. Or actually, I'll just find one in the book. Okay, you got it. And I'm hoping my computer doesn't spontaneously turn off, because that's happened a few times recently. Okay. Knights and knaves, okay. If someone can find a knights and knaves problem that has all of the pieces that they want to do, I will do that. Right now I'm having trouble finding one that has all of the particular. Okay. Alright, I got one. Here we go. Okay. So I'll just do this for now. So let's walk through how to do this. Okay, so sure, the website that he gave us, or the website that he got his on, was solid, so I'll just find one. I just don't want to do one with too many. They all have like 6, and that's too many. Right now I'm finding one with an or and a could. Um, okay, I got one. So I'm going to change the text on here. I'm just going to modify this so that everybody has a different letter so I can abbreviate. And now we'll start. Alright. Is everybody happy with this one? Alright, if this is good, then I will get started. Alright, cool. So, the key here is to start with one that you have a that says something very concrete, that says something that is either true or false. So you don't want to pick one with the or right off the bat. You want to say either this is true or this is false. So what we're going to start with here is Karen, because Karen has a very concrete claim where she's saying that Marge is a knave. So if Karen is telling the truth, which we'll start out by assuming that Karen's telling the truth, then we will look to see what happens when we assume Marge is a knave. Because if Karen's telling the truth, that means Marge is a knave. Otherwise, it's the other way around. So that gives you a foundation. So what we're going to do here is we're going to start with Karen. So basically, we're going to assume that what Karen said is true. And the way that I'm going to mark that is by putting a little, put a check mark next to the arrow. So if we assume that Karen is telling the truth, then what that means is Marge is definitely not telling the truth. So next we have to look to see what those assumptions mean in terms of the other people's statements. So if Marge is not telling the truth, we look up at Marge's assumption. She says Zoe and Betty are knights. If Marge is not telling the truth, that means one of three things can be true. Either Zoe and Betty are both knaves, Zoe is a knight and Betty is a knave, or Zoe is a knave and Betty is a knight. Basically, she's saying that they cannot both be knights. That's not gonna that gives us quite a few different routes that we can take. So rather than try all of them, what we're gonna do right now is look at let's see if we can look at a different quote. Okay, so under the we can look at Betty's statement. Betty says that Karen could say that Marge is a knight. So under our current assumptions right now, can Karen say that Marge is a knight? The answer is no, she can't, because Karen is a knight. Karen is a knight and Marge is a knave under our current assumption. So Betty saying that Karen can claim that Marge is a knight is false. So under this assumption, we can also see that Betty is a knave. So now we're going to see where that brings us. Randall claims that Betty is a knight or Karen is a knave. So let's look at our current assumptions. Either Betty is a knight or Karen is a knave. Under our current assumptions, that's not a true statement. Betty is not a knight, so that's not going to be true. And Karen is not a knave, so that's not going to be true either. So Randall is not telling the truth. So we can show that Randall, shouldn't be a B. So we can see that Randall is a knave as well. Now, if Betty were a knight and Karen were a knight, his statement would be true because he's given an or. So that means that only one of these two conditions if I can get my pen to point in the right place. Only one of these two conditions has to be true. Neither of them were here. So, therefore, Randall is a knave. So, going on, we only have to verify a couple more statements. We have to check, basically, all right, we'll look at, what we're going to do is we're going to assume that Zoe is a knave, and then assume that she's a knight, and see if we can find a flaw in the logic of her statement going either way. Looking at Maher's question. So with an or, it's not false if they're both true. Yeah, so you can kind of resort to a truth table kind of thing for that. So Randall's statement, here's what I'm going to do. Basically, if Betty were a knight, no matter what, that's going to mean that Randall is telling the truth. If Karen is if Karen is a knave, that's going to mean that Randall was telling the truth. But if both of them are incorrect, that means Randall's going to be a knave. You can think of Randall's statement in terms of like regular propositional logic as being B or not K. So either Betty is a knight or Karen is a knave. And so if you need to scribble down a little truth table to help get that sorted out, that's fine. So we have that. So now we're going to come back to our final assumption. Of Zoe saying, at least one of the following is true, that I am a knight or that Betty is a knave. So let's assume that Zoe is telling, let's assume that Zoe is telling the truth. So let's see. Let's go through each of the statements. At least one of the following is true. I am a knight, so that's true immediately. Or Betty is a knave, so that's also true. So Zoe's statement is true on two fronts. Now we have to go back and look at the last statement that was made that we haven't looked at yet, which is Marge's. Marge is saying Zoe and Betty are knights. Marge is a knave, so that means that Zoe and Betty can't both be knights. Any other situation will work. If Zoe is a knight and Betty is a knave, if Zoe is a knave and Betty is a knight, or if they're both knaves, that will make Marge's statement false, which is in line with her knave status. So let's look at that. Zoe and Betty are knights. The way that we've assumed here, Zoe is saying, or Zoe is a knight, and Betty is a knave. So that means that Marge's statement is false, because Betty is not a knight. That means that assuming Marge was a knave was correct. So it seems like just happened to go down the right path right off the bat here. What I will do is make the opposite assumption right now about Karen, but just to put this all into one, the answer that we've come into. Our knaves were Marge, Betty, and Randall. And our knights were Karen and Zoe. I'm going to try and move this lamp so that there's not a shadow every time I write. Okay. Hold on. So that's kind of annoying. We don't really have a place for it though. Okay, this will work. Oh, whatever. Okay, so what I'm going to do now is just show what would happen, because we can kind of see, we sort of got lucky, because the first assumption that Karen was telling the truth ended up kind of bringing us down this entire path. It got us all the way to Zoe. This was the first actual crossroads that we ran into. Going the other way, though, this just turned out to be correct. If we had started out assuming that Karen was not telling the truth, let's just see what would happen in that situation. If Karen were not telling the truth, Karen claiming Marge is a knave would have to be false. So that would mean that Marge was telling the truth. Next, we'll look at Betty again. Betty says that Karen could say that Marge is a knight. So thinking about what that means. First we'll see, can Karen say that Marge is a knight? The answer to that is no. Because Marge is a knight, Karen stating that Marge is a knight would be true, which violates her status as a knave. Also, Karen's statement here is something that has already been said, that we've analyzed. So she's saying here that she's a knave. So this is going to be, Betty's going to be a knave as well. So now we're going to look at Randall's claim. Randall is stating that Betty is a knight. Wait, hold on. I see Aiden's question. So when Marge says Zoe and Betty are knights, it doesn't mean they're both knaves. No. That's the tricky part about the ands here. Hold on. When Marge says Zoe and Betty are knights, if Marge is telling the truth, that means that Zoe and Betty have to be knights. However, any other situation will work if we assume that Marge is a knave. In the correct solution, we assumed Marge to be a knave. So that means that just Zoe can be a knight, just Betty can be a knight, or they can both be knaves. If we know that Marge is not telling the truth, then literally any situation can be true except for what she's saying. It's a lot easier, in my opinion, to narrow things down when you're given when you assume someone is a knight, because that means whatever they're saying is an assumption that you can absolutely make. Or I should say, when a person's telling the truth and they give an and statement, that basically gives you a strict guideline for what can exist in your hypothetical. And actually, now that we've shown that Betty is a knave, because Karen can't claim that Marge is a knight because that would be true and Karen's a knave, we're actually going to look at that statement that you just said, Aiden. Marge says Zoe and Betty are knights. Marge is telling the truth. This is like the conclusion that we've drawn so far coming down this road. If Marge is telling the truth, then Zoe and Betty both have to be knights. But we just showed that Betty is a knave, like necessarily, by this line of logic. So Marge's statement that Zoe and Betty are knights, knowing that Marge has to tell the truth, is going to be the nail in the coffin for this particular set of assumptions. The statement that Marge says, here, what I'll write is, this is not going to work. So that's going to be incorrect for sure. I'm actually going to do one more thing here. I'm going to make a Google Drive that I'm going to upload these papers to as I go. So sit tight for a second, and if anybody wants to prepare a particular question or a particular topic to do next, drop that in the chat, and I will get this set up. Just hold on a minute. And it'll be better resolution than this like garbage stream that's on the screen. Okay, so you got it. I see there are 8 people watching right now, so if there are any people that are not in the chat and you're trying to figure out how to chat, you just have to sign into a Google account. But if you're just sitting quietly and watching stuff, that's all cool too. Alright, so I am gonna make this folder. Nice job, LJ. I think you figured it out. Alright, so if there aren't any other questions on this problem, then I am just gonna upload this, and that's gonna be it. So hold on for a sec while I scan this. No one tell Randall I made him a knave. Okay. One. 104 mod 3 is 1. Because 102 is a multiple of 3. So, alright. Scanning right now. I hope. My printer isn't a piece of shit. Definitely 3. Gonna have to agree with Sebastian on that one. Okay. Okay, I'm just going to share this folder real quick with a link, and then we'll be ready to continue. Alright, I'm going to add one more thing to the screen. Ah, fuck, I'm dumb. Hold up. Alright. So okay, so does that link work for people? I want to make sure that's like viewable for people that are clicking it. Oh wait, no, I don't think it's viewable. Okay. Alright, I think I fixed the link. I might have to change it 1 second. Alright, so does that link work for people? Let me know and I'll move on. Alright, cool. So, next problem I'm going to do, someone texted to me. Dropped my mic, I'm stupid. Okay, so okay, so let's have a look at this problem. Alright. Okay, the one that was on the test about writing a logical argument using the rules of inference with the whole tuxedo dentist garbage, that problem was actually like deceptively easy, and everybody that, like the person that texted this problem to me, it looks like you actually got it right. Everybody got it right. Mr. Audi just kind of graded it in a sort of a wacky way, to say the least, without just not allowing the whole transitivity chain. I'm going to take a look at the Venn diagram problem real quick and explain exactly how that one went down. So, if you want me to do another, I'll find another proof problem in a minute. I'll find another proof problem in a minute. We can go through all the different, and I'll find one that uses several different rules of inference. But for now, I will look at this Venn diagram problem. So we have I'm going to turn off my disable low power mode.
Oh.
Alright. 20% of the population. %, read A and B, 5% read A and C, 4% read B and C. And 2% read all 3 news. So the first thing I'm going to do here is just go over exactly how to construct this Venn diagram. The key here, the most important thing that I can think of when constructing a Venn diagram from data like this is to work from the inside out. You want to start with whatever information they give you about people reading all 3 newspapers, and then just sort of like branch out from there. So what I'm going to do, darn, I think I lost it. Oh, here we go. All right, so what I'm going to do is go through each of these I'm going to go through each of these probabilities that are given, but I'm going to go through them in reverse order because they're kind of given from the most general down to the most specific. So my eggy ass Venn diagram here. I'm going to have this one represent newspaper A, newspaper B, and newspaper C. Also, the numbers that I'm going to use, I'm just, instead of using like 0.02 for 2%, I'm just going to write 2, because if it's like a percentage of people, we can just assume that there are 100 people and 2% of them read all 3 newspapers. That's going to work. Regardless of whether there's 100 people or 1,000 people, it's going to be the same percentage, and that's the goal. So the first thing that we're given is that 2% read all 3 newspapers. So this area right in the center, the intersection of circles A, B, and C, that's going to be 2 to represent 2% of people. The next one we're going to look at, let's look at this 4% read B and C. B is this circle out here, and C is this circle. If we just pretended the circle for A didn't exist, we'd be left with this little egg business in here. This here, this like, this eggy thing is the intersection of B and C. That's where circle B intersects circle C. It's like your regular Venn diagram that you see that's kind of got like these 2 circles that go like this, and this center part is their intersection. B and C intersect in this like orange area. So we see that 4% read B and C. So that means that this entire intersection is going to equal 4. It's going to represent 4% of the population. We already have 2 in there. So the remaining 2% are going to have to fit into this area. The reason for that is that the 2% of people that read all 3 newspapers, this 2% that read all 3, they fit this description of reading B and C. So when he says that 4% read B and C, the 2% that read all 3 newspapers are included in that. If I say I walk, bike, and swim, I'm included in a list of people that walk and swim. I'm included in a list of people that bike and swim. Just because I do this extra action or have this extra quality doesn't mean I'm excluded from this group. So these 2% of people that read all 3 newspapers are going to be part of the 4% that read B and C. So next up, in a similar fashion, we're going to look at the percentage of people that read A and C, this 5%. And in just the same way, that's this little area, that's this intersection of circle A and circle C. We saw that 2% of them, 2% of people read all 3 newspapers. If you read A, B, and C, you must then read A and C. So this 5% that read A and C, there's going to be a total of 5 in this little walnut thing, 2% of them are already here, so the other 3 are going to go right here. And that same quality is going to stand for this last one. Up here, it's going to be done in much the same way. Hold on. This is A intersects C. And this area up here at the top is going to be where A intersects B. Now, if the number of people that read A and B is 8%, 2 of them are here, so 6 of them are here. So that's where these center parts come from. Next, we're going to look at, we see 14% of people read C. That means that the sum of the numbers in this circle is going to be 14. We see we've got the 3, 2, 2 already in there. 3 plus 2 plus 2 makes 7. So the other 7% of that 14 are going to fit in here. I'm going to move through the other 2 pretty quickly. 16% of the population reads B, so the sum of the numbers in this circle is going to be 16. 6 plus 2 plus 2 is 10. So therefore the remaining 6 need to be over here. And then finally newspaper A, 20% of the population reads that. 6 plus 2 plus 3 is 11. So the remaining 9% is going to fit into that. So now we're going to look at how to deal with these, or I should say, there's one more important number that exists here. 20% of the population reads A, 16% reads B, 14, like all these percentages exist. But the number of people that live in a town is like 100% of the people that live in that town. So all these areas together, 9 plus 6 plus 6 plus 3 plus 2 plus 2 plus 7, all of that added together equals, I believe, 35. Let me check. 10, 20. Yeah, equals 35. So the other 65% of the population that lives in this town that isn't in this Venn diagram must therefore not read any newspaper. So outside here, if I put all of these in some universal box, 65% of people are going to be out here in La La Land, not reading any newspapers. Yeah, I'll do a quick problem like that in a second after I handle the other problems there. The other problems that are like part of this Venn diagram problem. So now we're going to find the probability that a person at random reads these different things. So 65% of the people don't read any newspaper, so A was none. And that's going to be, I'm going to write all my answers in red. 65 out of 100. And you can reduce these if you want, but I'm just going to give them unreduced. At least one. If you are anywhere in this Venn diagram, you read at least one paper. That's fair to say. Like all these statements up here describe people reading some single newspaper or some combination of newspapers, but all of those people read at least one newspaper. So this 35% of the population that was inside of our Venn diagram, whether they read one newspaper or whether they read 3, they all meet this criteria of reading at least one paper. So 35 out of our 100 people read at least a single newspaper. Now here's where we get interesting. Exactly one. If you're here, or here, or here, or here, then you're in some intersection of the circles and you read some combination of newspapers. That means that the only numbers that are going to matter here are the ones where you're only in circle A, or only in circle B, or only in circle C. So adding all of these together, we get if I'm not mistaken, 22? Yeah, 22 out of 100 people read exactly one. They don't read A and B, they don't read A, B, and C, they don't read no newspaper. They read exactly one. So that's going to be 22 out of 100. And move on to D, which is A, B, or both. So, I'm going to hopefully get this right because I couldn't do this addition on my test. If you read A, B, or both, that means you're in the A circle, or you're in the B circle, or you're in both of them. This, I'm going to outline this one. Let's do that in, I don't have any distinct colors that I haven't used yet. I'm going to just use light blue. This region right here. Actually, I'm going to get do I have highlighters? I do have highlighters. Okay. This region out here. Anything inside of this blue is inside of A, or it's inside of B, or it's inside of both of them. So this is going to be, the sum of all of these things is going to be the percentage of people that read A, B, or both. So 9 plus 6 plus 6 plus 3 plus 2 plus 22 is 28. 28 out of 100 people satisfy that criteria. Now we're going to look at 8, or E. This is the percentage of people that A, given that they read at least one paper. All right, so this one is interesting. If we, so this whole, like, the number of people that read A given that, what that means is that we know right off the bat that the person that we're finding, like the probability of whether they exist, they read at least one paper. We found up here the number of people that read at least one paper. That's 35. The number of people that read A, or the percentage of people that read A, just looking straight up at the problem, is 20%. 20% of people read A, and 35% of people read at least one paper. So, what that means is that 20% of this 35% read A. So 20 of this 35% that we've reduced our pool to because of this given that thing. Basically, this given that causes us to be able to reduce the number of people that we're considering when we're coming up with this fraction. So now we're looking at the number of people that read A, which was given in the problem as 20. So I'm going to come up with two more things here that aren't on the test, just to sort of like explain what this means. I'll say the probability that they read that a person reads newspaper C given that they read paper B. What that's going to be, basically on the bottom, we're putting the size of the pool that we've reduced our people to. In this case, it's going to be 6 plus 6 plus 2 plus 2, because that's the number of people that read paper B. So that's going to be 16. And the number of people that read C inside of this B circle is 4. So 4 people read C. within that circle B. Okay. I hope that I cleared this up. If anybody has any other questions, feel free to drop them in the chat while I finish everything up here. And I'm just going to go ahead. Actually, let me label this a little more. Okay, so I am going to upload this real quick. And so next up, we're going to do an induction proof. Okay, so scanning real quick. All right. Okay. So let me bring this light back on. All right, so I'm gonna look at texts real quick. See what's up next. Okay. Oh, there's a bunch of stuff here. Oh, someone asked me for 4B from that probability thing. Actually, we'll just do induction first and we'll come back to probability. Just remind me at some point to do that. Okay. Hold on. Okay. Also, I'm not sure that this got to everybody. The fact that I was doing this stream. So if anybody knows anybody who they think might benefit from this, or you know that has a question on something, feel free to let them know that this is going on, because I didn't really. I kind of just like thought of it yesterday, and so I didn't really have a chance to tell a super large number of people. So anybody that it can help out, be cool if it helped them out. Okay, so next we're going to look at an induction problem. So this one I can't really put on the screen, so I'm just going to write it out on the paper, and we'll do it that way. Okay, that's better. And I think I'm going to move my lamp again. I'm thinking this will work better because now it's no longer... Okay, so you can see what I'm writing under my hand as I'm writing it. Yes, sir. We're going to get this done plain and simple. Alright. So, given the following premises, write the general formula that you can prove using mathematical induction and complete the proof. Okay, so this is from an old test. The things that were given. Hold on, let me put the topic up here. Alright. So, the pieces of the formula that we were given here were 3 equals 1 times 6 I just got another text about binary subtraction. I will put that, I'm gonna get a little to-do list going so I know. Let me add a thing here. Eris medium. Alright, so what I'm going to do here, I'm going to put a little to-do list of the things that we're going to get to, or have done, and I'll put it on the side, and if anybody has anything that they want to add, or that they don't see on there, just let me know. Okay, so we're going to do induction. We'll do algebraic proofs. Do Boolean expressions, so rewriting things a certain way, or argument forms. Okay. Alright, so I'm going to just leave that over there. And then if anybody has anything that they don't see on there, just shoot me another text. And I will add it to there. I know there was a bunch of stuff at the very beginning. Actually, I'll add those to this real quick. We've got okay, I think that'll do it for now. Again, feel free to text me if you need anything. Alright, so induction, continuing on with this formula. Alright, so that, so on and so forth. So, man, that's bright. I guess you can see it fine when I just turn the lamp off completely. It kind of eliminates the shadow too. So I think I'm going to keep it like that unless anybody can't see it. Looks okay on my screen as it is right now. So I will just leave it like that for the time being. Someone look at Maher's question and see if they can find anything from the, because I don't have a list of the topics that he said in class. I didn't write that down. So looking at this, we're going to try and develop a pattern based on the things that we see here. So, hold on. Alright, so what we see is we're starting at 3 and counting up to some number. So we need to come up with a formula that we can represent on both sides here using, I'm just going to leave this camera on. Actually, I think I can ghost this a little bit. Oh, no. Okay, no, that actually looks good. Okay, hopefully this doesn't make everything too slow. Okay, we're good. So, we're going to come up with a formula for both sides of this equation that we can express in n. So, we're basically going to start at 3. We're going to, like we see like in all these equations, we're starting from 3 and we're counting up to some number. So this is basically starting at 3. If this is the first, if this is n equals 1, this will be for n equals 2. This will be for n equals 3. And we're counting up until we reach some final term, which if this was n equals 1, then this is n plus 2. If this is n equals 2, then this is also n plus 2. 3 plus 2, we know 4 plus 2, 5 plus 2, 6 plus 2, on and on and on, up until our last term, which will be n plus 2. So this aligns with what our formulas are here, because if this is, hold on, let me check to make sure we didn't say to start at 0. Okay, so this over here has to be for n equals 1, this for n equals 2, this for n equals 3, this equals 4. Okay, so we see that these formulas match up because this goes 3, 4, 5, up until n plus 2, which was 4. So that works for the left side. So now we have to have this be equal to something over here. Well, what's our pattern here? We have 1, 6, 2, 7, 3, 8, 4, 9. In each of these, we have a fraction. It's over 2 every time. In our numerator, we see our n appearing here, 1, 2, 3, 4. So we have n times n plus 5, it looks like, because we have 6, 7, 8, 9. We're still counting up by 1, just like n. So n plus 5. So now we have a formula that we can prove using induction. And so this is going to be true for all integers n such that n is greater than or equal to 1. And so this would be the first part of our answer. He asked for the formula that can be proved using induction. So this is our formula. Next, we're going to do the actual proof side of it. Oop. Oh no. I think this pen literally just ran out of ink. Oh, no, it's back. Okay. So now we've got this. So now we're going to do the actual proof. So we've got our formula over here. I'm not going to copy it over because I'm lazy. We're going to start with, there are 3 steps to the proof that we have to do. First, we have to show that our proof is true for n equals 1. So let's do that. Plugging in n equals 1, we're really just going to end up with this over here. We see we're going to count up from 3, 4, 5, up to n plus 2. So we're going to plug in 1 for n, plus 2 because it's our last term, equals 1 times 1 plus 5. So this is us plugging in n everywhere into our formula. You have to show, when doing this, you have to show the actual plugging in of n. You can't just use this simplified version from over here. You have to show where n is plugged in everywhere that you have an n in your formula. You have to show where it's going in here, and then you can start to simplify both sides, where you say this is 3 equals 1 times 6 over 2 equals 3, and then you can say that that's true. So that's good. Now we're going to show our, we're going to do the part where we assume that our formula is true for n equals k. So we're going to plug in this deal, and I'm going to show you that with a little bit of color coding. I'm going to do this part in, where's that pink? Okay. So p at k, we're going to plug in 3 plus 4 plus dot 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 plus k plus 2 equals k times k plus 5 over 2. So this is really all that's necessary for this step. It's just plugging in k into the formula. For the last step, we're going to do p at k plus 1 and show that this is true using our assumption that we just had. So writing all that out, if we go all the way up to the k plus 1th term, that's going to be 3 plus 4 plus dot 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 plus the term before k plus 1 is going to be with k, so we'll write that one. And then the last term that we'll have is going to be k plus 1 plus 2. So that'd be k plus 3. So all of this is going to be equal to this side of our formula over here with k plus 1 plugged in this time. Up here we plugged in k. Down here we're going to plug in k plus 1. So we're going to have k plus 1 and this will be k plus 1 plus 5 instead of k plus 5, and that will all be over 2. Now, this part right here that I'm underlining is our p at k. That's what we had up here. We assumed that this was equal to this, so now we're going to use that assumption here and replace what I've underlined in pink with this formula from up here. So k times k plus 5 over 2. So we're making this replacement using our p at k. All of that plus k plus 3 equals this whole mess over here, which is now k plus 1 times k plus 6, quantity over 2. And now you're kind of at liberty to do whatever algebra you want to show that these are true. So I will just math that out real quickly for you guys. Multiply both sides by 2, and you get k My bad, I can't do algebra. So this last step here is good. So we know that this entire proof is going to end in true by mathematical induction. And if you're Jose, you drop a little t in there too. Alright, so that's going to be it for mathematical induction. I'm going to scan and upload this, and we'll just move quickly on to the next problem. Okay, so next is going to be algebraic proofs. Hold on, that's scanning real quick. Oh, my printer just made some weird ass squeaky noise. Whoops. One second. I'll be right back. All right. Had to get some food. I'm not sure how me eating in front of a mic is gonna go over. Probably not super well. I'll probably mute when I do that. I'm gonna figure it out. Okay, so next we'll do an algebraic proof. These are pretty straightforward. The most tedious thing about these is remembering all of the different justifications for actions that there are. I think I'm just going to do... I'm going to do a problem from an old test again. Actually, if anybody has a proof that they want to see right now, feel free to shoot me a text. If I don't get anything, I'm probably going to do something along the lines of like the difference. Actually, I don't know, it's a little simplistic. If anybody has an algebraic proof that they want to see right now, shoot me a text while I look for one. Okay, so now this lamp's in my way. I can't see the screen. What am I gonna do? Well, I mean, actually, I'm going to bump this algebraic proofs thing down the list until someone sends me one that they want to do, because the one that I have right now is kind of like a broad question, so if anybody has a specific one that they want to send me, they can do that. Otherwise, I'm just going to move on to Boolean expressions and simplifying those with different rules. So that, I can pick one out of our book. Oh, shoot, I did not upload that induction PDF. Let me do that real quick. Or the Venn diagram PDF. I am slacking. Okay, so those should both be up now. Okay. So let's look at a Boolean simplification problem. So I'm going to cover Boolean statements and truth tables. Basically, all I'm going to do for this is actually, I'm going to knock out Boolean statements, truth tables, and circuits all in one here. So I'm going to find a good circuit from the book, simplify it, and turn it into a truth table. So I want a hard one. Okay. shit. I've been... Man. Thanks for calling me out, Ryan. Man, that was a goof. Yeah, okay, yeah, I've been talking just, I guess, to myself for a little bit. Quality. I turned it off to, eat an apple. I never turned it back on. What a goof. Okay, well, yeah, shit. Okay, so... Oh well, yep, that's the mute button got me. I hope it's, been okay to follow so far. Damn. I'm gonna just continue here. I'm hoping that this is all making sense even without audio, and that you guys weren't like waiting for audio to come back, and like we're alt tabbed away or something. Sorry for the goof. Man, all right. True, Ryan. Okay. Whatever. Nah, I'm just bad. Oh man, so nobody. Yeah, I moved the algebraic proof down to like I asked if anybody can find one that they want to send me. That's fine. But I couldn't really find one in the old books that I thought. Like basically, if anybody has a question about algebraic proofs, I'd prefer to be like sent a question to do rather than just pick a random one. I can't believe I was muted for so long. I feel like such a goon. Okay. So this is the Boolean expression that's come out of this whole big fat circuit. One second, I have to respond to something. All right, so we're gonna simplify it in just a second. Okay, so I'm gonna walk you through simplifying this now. Assuming my audio's on. I didn't fuck that up. Basically, to simplify these, we're just gonna work from the inside out. We're gonna get it into ands and ors as much as possible. We're gonna get rid of the knots. Turn move as much as we can around. And I'm just going to show you how that works. So, here, one moment. Okay. Okay. So I'm going to take this side here and simplify it as much as I can. So first I'm going to distribute this this part over here with De Morgan's. Okay. Ugh. Sorry, I keep disappearing. A bunch of people just messaged me all at once. Okay, so distributing this, we're just going to take care of this part over here first. That's going to give us if we're going to write everything in terms of OR. Once we do that, then we can kind of we can condense everything and we can move things around using the different rules of Boolean logic that we can find. I'm going to pull those up real quick. So this will become